Hello, everyone. Today, I have the honor to tell you about a project done by my intern, Milli, who couldn't be with us today, in collaboration with her PhD advisor, Hardt. As you know, most recommendation systems today are based on engagement optimization. Therefore, they recommend content that the user is more likely to engage with. Engagement can mean many different kinds of behaviors. For example, on Twitter, here we have a user could interact in different ways, such as click, reply, retweet, quote, etc. And as you can imagine, aggregating all these different behaviors into a suitable objective is often very difficult. What we propose to do is to optimize directly for value. And we define value as the user appreciation for the content. However, this is a very vague construct. It's underspecified, and most important, it cannot be observed directly. This is also true for other disciplines. We can draw a lot of parallels with especially social sciences, where they had to measure this kind of vague theoretical construct for a long time. For example, socioeconomic status, quality of life are some of the examples. Therefore, when we are trying to make a measure of value in our construct, we can rely on the lesson learned from these other fields. Indeed, there is a whole field of measurement theory that provides us with established approaches to creating measurement of theoretical construct and assessing their validity, as we'll see in a minute. Okay, so how is measurement theory helpful here? So using measurement theory, a theoretical construct, so for example, socioeconomic status here is operationalized as latent variable and related to observed variables via a latent variable model that we can represent as a Bayesian network here. And then in this example, we can define the socioeconomic status as by the observed variables, education, income. So the latent variable model here defines a joint probability distribution over these variables. And so we can imagine how we can assign an individual socioeconomic status by using, again, in this example, education, income that are observed. Okay, now we want to do the same for our construct. And so we want to see how we can operationalize value. So as before, value is going to be a latent variable in a latent variable model that relates to the things we can observe, specifically user behavior. And so, for example, here we have listed some behaviors that are possible in Twitter. And it's important to know that from now on, all variables, including value, are considered binary values. And so the end goal is to learn the distribution of value-given behaviors and then use this distribution as a plugin replacement for the optimization task. There is a lot of literature and established frameworks to talk about validity of measurement that includes some of the criteria listed here. And these are examples from the standards for education and psychological testing. In the paper, we go in details on what validity might mean for a recommender system. And so the big question here is, of course, how we get the joint distribution of the latent variable model, which is what we're going to talk about next. And this is the meat of our contribution, a way of designing this model. So let's step back for a moment. In recommender system, even if there is usually no way of directly measuring value, there is some type of explicit feedback that provides or might provide strong evidence of value. So for example, in Twitter, you can actually click on a tweet and there's an option to see see less often. And so this is pretty explicit in the sense that if a user clicks see less often, we can assume they don't really value it. And so we call a variable a for which we know the distribution of value given a an anchor variable. And our key insight here is that having just one anchor variable will allow us to identify the full joint distribution of value and behaviors. It's important to note that this anchor variable is often very sparse. Going back to the Twitter example, there are not many people using this feature, maybe because people are not aware of that, or maybe because they don't want to like spend the extra time to give this type of feedback. However, the interesting thing about this approach is that even having a signal that is so sparse, so it's too sparse to optimize directly for. However, it is useful for learning how reliable the other signals are. And we're going to see that in a few slides. So maybe let's now talk about the conditions under which the joint distribution is identified. Here, V is value, A is the anchor variable, and B is all other observed behaviors on the platform. So the first assumption is that the probability of seeing the anchor variable is different depending on whether the Twitter is valuable or not. Then we have an assumption. The second assumption is that there are no children in the base network for the anchor variable. So if the base network is drawn causally and the anchor variable is a negative signal, this sometimes just means that there are no other behaviors that are possible after the anchor happens. So to give a concrete example, on Twitter, when you click on show less often, the tweet literally disappears. So you cannot interact with that anymore. And finally, the third assumption that we call one-sided conditional independence relies on the anchor variable and being a strong signal. So what it says is when the anchor is present, which again means, for example, in our case, the person clicked on show less often, the probability of the tweet being valuable does not depend on other variables. In particular, it does not depend on other currents of anchor beside value. And if you think about that, it makes sense. Again, because the assumption is that this signal is very strong. If someone clicks on see less often, we can be highly confident that they do not value that content, regardless of what actions they have done, if they click on that before or replied. Again, it's important to stress again that this assumption is one-sided because the anchor is usually very sparse. And so in some cases, it might be because given this kind of feedback is high effort, or as I mentioned earlier, not a lot of people even know that this exists. Okay, so given the assumption we just talked about, this is our theorem that this four distribution that we're going to talk now uniquely identify the distribution of value given anchor and behavior. And so the four distribution we need to define are, the first one is the prior on value that we set to uniform to 0.5 in our case. Then we have the probability of value given the anchor. So what is the probability of value after if a user clicks on show less often? So this, it's a modeling assumption, and in our case, we put this equal to 0. Finally, we have the joint distribution that that can be estimated empirically from data. And finally, this is the trickiest one to get, and is the distribution of all the parents of the anchor except value, given value. And we'll describe in the following example a little better So let's see an application at scale on the Twitter machine learning-based push notification. So that's the workflow. A user might get a push notification on their phone saying, X person liked a tweet or Y person posted a picture or whatever. The user can click on the notification and is brought to the content. At the same time, if the user was already in the app, something will show up on a notification tab where they can click and go to the content. And after that, they can decide to engage or do whatever with the tweet. They can also come back to their notification tab and take their time to show this kind of notification less often. Also, at any time, they can opt out of notification altogether. So now we want to formalize this workflow as graphical model. And so we are going to start assuming the user is in the notification tab, and so they can click on the notification. As before, the user could open a notification if they get one, if they're not already in the app. And an arrow from a node to a box means that the node is a parent of every item in the box. So after they click on the notification, they can interact with the content with the tweet in a variety of ways. And then, as said before, at any time they can opt out of the content. That's why we have another node there. And finally, we add our anchor variable, which is show less often, as a child of notification tab, because you have to go back to notification tab to do that. Now, I'm going to talk more later about these two extra arrows. They're technically not needed in the sense that a person can click show less often without clicking or opening the notification first, but we'll see why is that a very important assumption in our modeling. And finally, value is apparent on everything except notification tab. Cool. Now we want to assess the validity of our model by using something usually called evidence-based on internal structure. And what it means is we want to look at relationships between variables and see if it matches the idea we have about a problem. So we start. So here we list some, behaviors, and we are going to list the probability of value being equal to 1 given this behavior. So our first modeling approach is, and like we are going to use this as a baseline, is a naive-based model, which simply assumes there is no structure and all behaviors are conditional independent given value. As you see from these numbers here, this is very inaccurate assumption because almost all the inferences are negative that have been clicked to 0. Now, before going into the full model that I described earlier, we want to try this one, which is easier from a modeling perspective because show less often our anchor variable here has only one parent beside value, which is ntab. And so this is pretty straightforward to compute, and then these are the results. And what we see here is that it doesn't really work because, as a reminder, our prior on value was 0.5. So almost all behaviors here indicate that all these probabilities are smaller than the prior. So this also doesn't seem to make sense. Now, as I mentioned earlier, we were technically not required to click or open the notification before clicking on show less often, which is why we remove these two arrows. However, we noticed that users are in practice are very likely to do so. And probably is because they needed to gain information about the content that was recommended to them before making an assessment and deciding if they want to click on show less often. And so we found that explicitly adding this connection, so again, these two arrows that we have added back, was critical for making reasonable inferences. So now this is trickier because what we want to compute is now the anchor variable has multiple parents beside value. And so the distribution that's on top right, so the probability of all the parents of the anchor variable besides value, given value, this is trickier to compute. And so what we have done is we have, and so the reason is because we need to be able to estimate the probability of click or open given value. And so we have estimated that by using two sources of historical data. The first one has recommendation chosen at random, and the second one has algorithmic-driven recommendation. And so what we're assuming here is, so we can write the law of total probability and for each of them. And the left-hand side can be estimated empirically by looking at behavioral data. And then we are going to make an assumption about the prior probability of value. And we are going to choose it in a way such that the probability of the algorithmic recommendation, the probability of value of algorithmic recommendation is higher than the one at random. And if this is a causal based net, this is equivalent to assuming that the only difference between these two is an intervention on value. And the rest is the same between the two. And so now we can solve the two equation for the required distribution. And what we obtain is it's very interesting actually, because these numbers make much more sense, and we can see how different behavior correspond to different probability of value given behavior. So for example, if you retweet, it's the probability is higher if you only click. And the model also learns a lot of interesting fine-grained inferences. So for example, offers a higher value for open versus click, given that the user is active. And the reason is if a user just clicks on a notification from the notification tab, we cannot really attribute them being active to the notification itself because they were already in there. And so in conclusion, I want to offer some of the takeaways from our approach. So the first one is, it forces the design of the system to actually think about what value is or what value means. We also have, it's easy to give value different meaning by choosing a different structure of the Bayesian network and the anchor variable, as we saw an example earlier. And then this, we offer this principal method for identifying joint distribution of the latent variable model, which can be re-estimated at any point instead of manually fine-tuning pieces. And then, assess with very established approaches the validity. And we only saw one today, but in the paper, there is many more that I invite you to read. And so that's it, everything I have for today. Thank you very much.